Okay, so anything optics has to do with the science of light. So when somebody says optics, just think about what? Light. And light itself is the reason why you have the belief that you can see. Is a type of wave that stimulates the sensation of vision. You get that? So for light, it is important you can analyze everything about what? Mirrors, curved mirrors, prisms, lenses, and their various what? Applications. Now, because this is a summary class, I will just what? Be as direct as possible. Sure you get that. Okay, for plane mirrors, for plane mirrors. So I'll give you their properties and I'll give you the applications and also the formula we make use of in plane mirrors. So a plane mirror is just a viewing mirror, and the properties of plane mirrors include: number one, image distance. Image distance is always equals to the object distance. Image distance equals to object distance. Then we have what? Image size is equal to the object size. And practically, if an object happens to be running in front of a plane mirror, the image of that object is also going to be running. So if an object goes closer to a mirror, the image itself comes closer to it. So which means we can assure, it is safe to say, the image speed is equal to the object speed. The image speed is equal to the object speed. Similarly, the magnitude of the what? Velocity of the image will be equal to the magnitude of the velocity of the what? Of the object. So I meant to write speed here, not size. Object speed. But it would be wrong to say the image velocity equals to the object velocity. Don't forget, velocity is a vector, and we should be concerned both about the size and also the direction. The direction of the image and the object are always opposite to each other. So number four, we always have lateral inversion. Laterally inverted image. So which means if an object stays in front of a mirror, the object, when compared to the image, are going to be having what? Lateral inversion. The left of the object becomes the right of the image and vice versa. Then number 7, I said 7, number 5. Number 5, what do we have? We have a virtual image. The image form is always virtual. So there is a way to quickly distinguish between a real image and a virtual image. For all real images, they can be focused on a screen, while virtual images cannot be focused on a screen. Now, using that logic, some people will still mix it up, being able to tell what is real and what is virtual. Okay, a better way is this. If you are an observer, if the image is formed at the side of the observer, the image is real. But if it is formed at the opposite side of the observer, it is what? Virtual. As somebody who stands in front of a mirror, you are the object and the observer at the same time. Now, where do you see the image? The image is within the mirror. You cannot access it. Because you cannot access it, you won't have a room to even be able to what? Focusing on the screen. So that means what? Such image is virtual. But we have images that are real too, but that can be produced by a plane mirror. That can only be produced by a curved mirror. We'll get to that. So these are the properties of what images formed by a plane mirror. Virtual, um, it is okay, good. There is also 1, 6. The image is always what? Erect. Or you use the word what? Upright. So these are the summary of what images formed by a plane mirror. Okay, so we have other situations of plane mirror. Inclination of plane mirror. Inclination of two plane mirrors. Inclination of two plane mirrors. So in an exam setting, there are just two things they usually ask when it comes to what inclination of plane mirrors. Number one, they ask for the number of images formed. Number of images formed. So when you place an object in between two plane mirrors that are inclined at angle theta, the number of images formed, which is written as what? Ni, will always be equals to 360 degrees over what? Theta minus 1. 360 over theta minus 1. Please always take note of that. Number two, they can ask you for deviation. If a question asks you for angle of deviation, it is always equals to what? It is always equals to 2 theta, twice the angle of inclination. And number three, they can ask you for what is it called? Final reflection, or let me put it this way. If this is a mirror here and this is another mirror, say this is mirror M1 and this is mirror what? M2. An incidence on mirror M1, we always produce a reflection which automatically becomes an incidence to mirror M2. So if you draw a normal to that too, it will produce what? Another what? Reflection. So if this is the initial angle of incidence I1 on mirror M1, and this is what? Angle of incidence I2 on mirror M2. So always know that what? I1 plus I2 is always equals to theta. It's not necessary to have this formula in your head. It's something you can always analyze from this diagram, but it makes it faster if you know this. So similarly, R1 plus what? R2 is always equals to theta. Alright, another thing you need to know is the law of what? Reflection. In reflection, the angle of incidence I is always equals to the what? Angle of what? Reflection, R. So please always know that I is always equals to R. That's a law of what? Reflection. And again, the line of incidence, the line of normal, and the line of what? Reflection are always meeting at the same point and also lying on the same plane. Please note that. Alright, then that takes us to parallel mirrors. Parallel mirrors. I hope you can hear me. Can you confirm you can still hear me?
Yes, sir.
Okay. So, parallel mirrors. Parallel mirrors are mirrors whose line of action, whose line can never meet. The two mirrors can never meet each other. Okay. Say we have this to be a mirror, and this is what? Another mirror. Okay. The two lines I've drawn here are parallel to themselves. So you have this to be mirror M1, and this to be what? Mirror M2. and from what you can see, their reflecting surfaces are what? Are parallel to each other. So which means if you have an incidence on mirror M1, it produces a reflection on mirror M2, which serves as an incidence to M2. Then again, that bounces back as a reflection to what? Mirror M1, which also serves as an incidence to M1. Then this continues to go on in that manner. So which gives you room to see multiple images of an object when placing between parallel mirrors. Do you get that? Now, in an exam setting, what can they ask you? What they can ask you for parallel mirrors is the number of images formed. So just know that the number of images formed here is infinite. You can have infinite number of what images formed for parallel mirrors. Now, you can also be asked for different positions of images, but at JAMB level they won't have such questions. So for now, I'm going to what? Pause on that. So they won't ask you such what? Such questions. Alright, so that's for plane mirrors. So the next we have curved mirrors. Curved mirrors. Curved mirrors. So like I said, this is a summary class. I just need to give you the summary, then solve some questions. So in a situation while we are solving problems and they happen to be what I have not touched, fine. I'm going to use the question to explain it. Alright, moving on. Just hold on. Alright. So, curved mirrors can be said to be concave or what? Or convex. When something is concave, from your line of view, it is depressed. If you are looking at this thing this way, if this is your eye and you're looking downward, what you are seeing is a depression, so it is concave. If this is your eye and you're looking at a surface like this, what you are seeing right away is what? Convex. So the word convex, you can always relate it to something, a surface that is swollen. So once you remember a swollen surface, then you can easily tell what is convex. For instance, most people's forehead are what? Convex in nature. Then we have concave. Concave is like a depression. So let's just say hollow. Good. That's a better hollow surface. A hollow surface is a concave surface. So okay, please give me 5 minutes to really attend to something. Just hold on. Okay, I'm back. So, like I said, a concave surface is always what? A hollow surface, while a convex surface is a swollen surface. For if I give you something like this and I ask you, is it concave or convex? You can't answer that question yet, except I ask you the position you will be standing. Okay, look at this. If this is shaded for a mirror, Definitely this side is the reflecting surface, the viewing surface. So if the left hand side is the viewing surface, that automatically makes this mirror a concave mirror. So this is concave. You get? So similarly, if you have something like this, if you have something like this, and this side is shaded, as an observer who stays at this point, looking directly into this side, what you are seeing is a swollen surface. So because it is swollen, that makes it to be what? Convex. So what are the things you need to know about concave and convex mirror? I will just explain one or two terminologies which we are going to make use of. Now, say this is what? A mirror, a curved mirror, and this is a line. Let me draw that again. All right. So if this is a concave mirror, if this mirror is completely drawn like a circle, if this were to be a complete circle, would have had something like this, which means we expect the circle to have a center. So the center here is C, and it's called the center of curvature. Then here we have what? A point here in between the center of curvature and the pole of the mirror is called the principal focus. So C is the center of curvature of the mirror, F is the principal focus of the mirror. So the principal focus is is a point where every line close and parallel to the principal axis converge to for a concave mirror. This line you are seeing here is called the principal axis. The principal axis. From here to here is called the principal focus. That is, the gap between the principal focus and the pole is called the focal length. This focal length. Geometrically, this is also equals to F. So that means the gap between C and pole, which we usually call the radius of curvature, like this gap here, is the radius of that circle. So the radius of curvature is equals to what? 2F. Alright, so we have mirror formula. So we have mirror formula. Mirror formula, we have 1 over U plus what? 1 over V equals to 1 over F. So where U itself is called the object distance, V is called the image distance, and F there is called the focal length. Okay, then we have magnification is given as what? V over U, that is the image distance over the what? Object distance. Magnification could also be written as what? VH over UH. So VH is itself is called the image height. Or you can simply say size, while UH is called the what? Object. The object height, or you can also say size. In some texts, you'll see a negative written beside what? Beside the formula. The negative there is to help the convention in a certain way. It's not necessary for you to have that there, provided you know what you're doing. So the two formulae you are using, like I said, are m equals to v over u, and what, 1 over u plus 1 over v equals to what, 1 over f. So the convention you are going to take note of, the convention used. So just note that what, real is positive, real is positive, virtual is negative. So I repeat, real is always positive while virtual is negative. Now what do I mean by that? Okay, e.g. for v, which is the image what, image distance, so we can say v equals to positive for real image, while v is negative for virtual image. So you can see that v is positive for real image, virtual is negative for virtual image. Now another case you need to what, think the convention for is focal length. For focal length f, is positive for real focus, Now where do we consider refocus, or where do we have refocus? For concave mirror, if you are dealing with mirror, or convex lens if we are dealing with lenses. Then f is negative for virtual focus, So what mirrors or lenses are virtual focus? Convex mirror has a virtual focus, while what, concave lens also has what, a virtual focus. Now in order to help you visualize this, I'm going to make an example, okay, by drawing a diagram. Now look at this. Somebody tell me, which mirror is this again? I'm listening. Which mirror is this again? A concave mirror. Good. So this is a concave mirror. Now if you watch, if I am to complete the circle to this thing, it's going to be completed in this manner. If we were to have a complete what, circle for this, so which means we expect the center to be here. Good. Now let me ask you, as an observer, where do you stand? Are you standing in region A or region B? As an observer, where are you standing? A or B? Come on, that should be a chorus answer. Did he say A?
Yes, sir.
Alright, that's correct. So it is going to be what? A. As an observer, you are standing at position A. So now that brings us to the definition of, now look at this. As an observer, you are standing here. No, not object, observer. Since you are standing on the left hand side of this mirror, the principal focus is at your side. You remember I said one way to distinguish between real and virtual is that real is always formed at the side of the observer, while virtual is always at the opposite side of the observer. Since the principal focus of a concave mirror is at the side of the observer, that automatically makes it what? Real. Okay, now watch another case. Look at this. This mirror here is a convex mirror. Now the reflecting surface is on the right side, which means the observer should be at this side. This is the observer here. Now if we were to complete the circle to this mirror, like if we were to make it to complete a full circle or a sphere, it is going to seem like this, which means the center of the circle would have been here. Good. So since the center of the circle will be there, the principal focus will be here. Now you can see that the focus is on the left hand side, whereas the observer is going to be on the right hand side. Since it is formed on the opposite side of the observer, that makes it what? A virtual focus. So the conclusion is that what? F will always be positive for concave mirror, while what? F will be negative for convex mirror. So always take note of that. The reverse is going to be the case for lenses. For convex lenses, it has similar property to concave mirrors, while for concave lenses, it has similar properties to what? Convex mirror. Alright, so keep that because we are going to need it while solving problems. Then another thing we'll need is ray diagrams. So we have ray diagrams. So what a ray diagram does is it reviews the it helps you review the properties of the image. It gives you a visual representation of what is happening about what? The image with respect to the object. So for curved mirrors, for you to understand it, I'll put it in a case study. So we have a case study of images formed by concave mirror. So we have case 1. Now for you to understand better, let me sketch something here. Now this is a concave mirror here. Then we have this to be principal axis. Principal axis is an imaginary line that runs through the optical center, the center of the mirror. So we have here to be the principal focus, and here we have what? The center of curvature. Sorry, this is an error. This is a convex mirror. What I intend to draw was what? Concave mirror. So I'll draw that again. Okay, so here we have what? A concave mirror. So we have several situations. We can have an object standing at position A here. Position A implies that the object is behind the center of curvature. We can have the object standing on C itself. This means the object is at the center of curvature. The object can also exist between the center of curvature and the principal focus. The object can happens to be on the principal focus itself. And this point here is called pole. The object can exist between the pole and the principal focus. And last case scenario is that the object may not even be in the vicinity of the mirror. It may be far away from the mirror, which means the object is at infinity. So that gives us about 6 case studies of the ray diagrams for concave mirrors. So we have case 1, object behind center of curvature, meaning the object somewhere around here. Case 2, object on center of curvature, meaning the object sitting here. Case 3, object between center of curvature and the principal focus. So you can easily tell where the object is, somewhere between F and C. Case 4, object on principal focus, that is object sitting on F. Case 5, object between pole P and the principal focus. So meaning the object is within the focal plane of the mirror. And lastly, we have case 6, which is object at infinity. So meaning the object is not in the vicinity of the mirror, is far away from the mirror. Okay, so for all these 6 cases, it is important you can tell the properties of the images formed. So we have case 1. Object behind center of curvature. So I'll give the properties of the image form, then I will explain why it is so. I only draw one ray diagram here. There are rules for drawing ray diagrams which I need to explain to you, but let me give the properties first. The properties of the image font. Okay, hold on, let me quickly add this person to the class. Good. So the properties of the image font. Number 1, the image is always inverted. Number 2, the image is always real. Number 3, the image is always diminished. Let me add this person to the class. Okay, the image is always diminished. Number 4, the image will always be formed between the center of curvature and the principal focus. Let me explain why it is so. Okay, but before that, quickly take this as the rule for drawing ray diagrams. Rule for drawing ray diagrams. So the number 1 rule is that any ray that goes parallel to the principal axis, we always pass through the principal focus after reflection. A ray parallel to the principal axis, is always, okay, passing through, or let me reframe that. Any ray parallel to the principal axis will eventually pass through the principal focus after reflection from the mirror. So this is what I mean. If you have this to be a concave mirror and you have this line here to be principal axis, okay, then you then have what, this point here to be principal focus and this point here to be center of what, curvature. The rule is telling us that if you have a ray that goes parallel to the principal axis, we all expect the ray to be reflected after meeting the mirror. It's telling us that the reflection will not just go anyhow. It will always pass through the what? Principal focus. Can you see that? That's the rule. Then number 2 of the rule for drawing ray diagrams. Number 2, any ray that passes through the principal focus must go parallel to the principal axis after reflection. Now this rule is just a converse of the first rule. They seem alike. It's like when you invert what, rule 1, you get what, rule 2. Now let me explain using this diagram. If this happens to be the concave mirror and this line here happens to be the principal axis, okay, now this point here is the principal focus and this other point here is what, the center of curvature. What the rule is telling you is that if there happen to be a ray that passes through the principal focus, this is me drawing a ray that passes through F. Now watch the arrow. The arrow indicates that it is an incidence, and we expect a reflection. It's telling us that the proper way to draw this reflection is to draw it parallel to the principal axis, since the ray passes through the principal focus. Can you see that? Now if you look at the one I drew first and the second one I've drawn, you can see that they seem alike. The only difference is the direction of the arrow. Watch. In case 1, the incidence is parallel to the principal axis and the reflection goes through the focus. In case 2, the incidence passes through the focus and the reflection goes parallel to the principal axis. Can you see that? Good. So then we have rule 3, which is the last rule for drawing the ray diagrams. Number 3. Any ray that passes through the center of curvature will always be reflected along the same path of incidence. Now let me explain this using a diagram. That's the only way you can get it well. Now say we have this to be a concave mirror, and you have this to be a principal axis. Then on the principal axis you have a principal focus F and a center of curvature C. What this guy is telling us, or this rule is telling us, is that if you happen to have a ray that passes through the center of curvature C, now watch the arrow. The arrow indicates an incidence, right? It's telling us that there will be a reflection, but the reflection will still go back along the path of incidence. Let me use a different arrow for that. The reflection will go back in this manner along the same path of incidence. Can you see that? It will go back along the same path of incidence. So incidence and reflection are along the same pathway. The only difference is the direction of what? Of flow. So to draw a diagram, we need any two out of the three is sufficient to draw the ray diagram. Any two out of the three rules, are you there, is sufficient to draw the ray diagrams. So you can use rule 1 and 2. You can use rule 1 and 3. You can also use rule 2 and 3. You don't have to use the 3. So the summary again: 1, when a ray passes through, when a ray goes parallel to the principal axis, the reflection is always along the always pass through the principal focus F. Number 2, when a ray is incident along the principal focus, that is, if it passes through the principal focus, the reflection goes parallel to the principal axis. And principal axis is always this imaginary line here. This imaginary line you can see here that passes through the center of the mirror. And number 3, when a ray goes through the center of curvature, the incidence is always along, the reflection is always along the same path of incidence. Please note this. I'm going to use this to draw just one ray diagram. For instance, the one that resulted into me writing the properties of the image formed when an object is placed behind the center of curvature. So I'm going to do that now. Okay, here we have a center. Here we have a lens. Sorry, not a lens, a mirror. To be specific, a concave mirror. And here we have the principal axis. Now watch. I'm about to show my principal focus. The principal focus will be somewhere around here. This point here, which I label P, is called the pole. This F here is the principal focus. Now watch. When you're about to draw the center of curvature, be careful. Now look at this. If I place the center of curvature at a position here, it means I am not considerate enough. Why? Because the distance here seems too far away compared to the distance here. Can you see that? I'm not saying you have to do your measurement every time, because it's not necessary you draw to scale for you to arrive at a result. But when you are positioning, it's good you do good positioning so that you won't end up having a wrong conclusion. So How best should I position my what? My center of curvature somewhere around here. Can you see that? It is justifiable for me to place it here. The gap here is looking similar to the gap here. Can you see that? So now we are considering an object positioned behind a center of curvature. So this is an object here. It's positioned here. Okay. Now this is somebody standing behind a center of curvature. Now, what does rule 1 state? Rule 1 states that when an object, when a ray goes parallel to the principal axis, let me show you again. When a ray is parallel to the principal axis, the what? The reflection will always pass through the what? Focus. Alright, so let's make use of that rule 1. So, I will draw a ray that will pass through, that will go parallel. Now this is me drawing a ray. Now see where I'm starting from. Starting from the head of the what? Of the object. So I'll draw a ray parallel. Zoom. That doesn't seem parallel. I'll clean it. Let me draw it again. That still does not seem parallel. Alright. So fantastic. So here we have a ray that seems parallel to the principal axis, and according to the law, it should be reflected. How should it be reflected? Through the principal focus. So I'll draw a ray through F. That doesn't seem passing through F. Let me do that again. I'm not using a ruler. Okay. Or let me use a proper line. Let me use a proper line instead of drawing it. Okay. We're gonna have something like this. Good. So I just drew a line that will pass through. The line may not be visible enough. Let me increase the contrast of the line for you to be able to see it well. Okay, let's increase the thickness of the line. Okay, let's increase the width of the line for you to see it well. Fantastic. Good. So can you see that? I just used a ray that is what? Parallel to the principal axis, and it goes what? It goes through the principal focus after reflection. Now I'm about to draw another ray. Now since I've started using a proper line, let me clean this so that we can draw a better what? Parallel line. Just hold on, guys. Alright, let's do it this way. Let me take this here to the head of the object, and this now. Okay, good. This is better. So you can see we have a ray that goes parallel to the principal axis. Then the reflection is what? Passing through the principal focus. Now, is that sufficient to reach a conclusion? No. I've used rule 1. Let me use rule 2. Rule 2 is telling us that what? If a ray goes through the principal focus, the reflection will be parallel to the principal axis. So, from the head again, from here, I'll draw another ray that passes through the principal focus. Okay? Let's do this. I have okay, so let's do it this way, and I want it to pass through the principal focus, so I'll do this. Can you see that? So that is the ray from the head passing through the principal focus. Then according to the rule, it should go parallel to the principal axis. Now let's make it parallel. I will draw a ray, the reflected ray. Okay, I have hold on. I needed it to be perfect. That's why I'm using these lines. Normally I could have just used my pen. I want it to be parallel. Now can you see that? So if you watch closely, you will see that for the first one, this is the part where it goes like this, then it passes through the word principal focus. Can you see that? Then the second one, it goes like this, that's the incidence, then it goes parallel to the principal axis. Now I'm interested in the two reflections. See the first reflection here, 1. See the second reflection here, 2. See their point of meet. Can you see that?
Yes, sir. Sir.
Yes?
Please, I did not get the second one. When you started explaining the second rule, the drawing you did for them.
Okay, I will explain them. Right.
Yes, sir.
Alright. So the first rule states that when a ray goes parallel to the principal axis, this is me drawing a ray parallel to the principal axis. After getting to the mirror, it gets what? Reflected through the principal focus. That's the rule 1. Can you see that? Then rule 2. I'm starting again from the head of the what? Object. I will draw a ray. We have a ray passing through the principal focus. Incidence is telling us that the reflection will go what? Parallel to the principal axis. So that's rule 2. So now that you have rule 1 and rule 2, you have a point of coincidence between ray 1 and ray 2. So look at the point of coincidence. This is the point of coincidence. Now, how do we know which part of the body of the object is there? The part of the object that will be there will be the head. Don't forget that the two rays were coming from the head. And their reflection meeting at this point will mean that the head of the object, of the image is there. So we can see that the image is here. So based on what you can see, let me redraw that. Now, can somebody compare the object and the image? Tell me what you can see. Let's start from the size. Compare the image to the object. What has happened? What do you observe?
The object is bigger than the image.
The object is what?
Bigger than the image.
Open your eyes very well. You said the object is bigger than the image?
The image is inverted.
Wait. Calm down everybody. Let's focus on the size first. On the size. The image, is it bigger than the object or smaller than the object?
Smaller.
Thank you. The image is smaller than the object, which is a conclusion that what? It is diminished. Do you all agree?
Yes, sir.
Good. Now let's talk about the orientation. Now, is it erect or inverted?
It's inverted.
Thank you. So it is inverted. Now, let's talk about the nature of the image. We want to be able to tell if the image is real or virtual. Based on what you can see, is the image real or virtual? If you don't know, tell me you don't know.
So it is a real image.
It is a real image. Do you all agree with him that the image is real?
So I don't understand how the image is real. How do you know
Fantastic.
if an image is real or virtual?
Fantastic. So this is what you do. For you to tell if an image is real or virtual, the first thing you need to do is ask yourself, where would I be if I were to be the observer? As an observer, tell me, are you going to stand in region A or region B? As an observer, where are you standing?
Region B.
You are telling me that you are going to stand at the back of a mirror. Is that what you are telling me?
Region A.
Okay. As an observer, you are standing in region A. So, since as an observer you are going to be in region A, is the image formed at your side? Yes or no?
Yes, sir.
Yes.
Good. Whenever the image is formed at the side of the observer, it is real. Do you understand the logic?
Yes, sir.
Fantastic. So the image is what? Real.
Okay.
Now let's talk about the positioning. How do you explain the position where the image is formed? We know where the object is. The object is behind the center of curvature. How do you explain the position of the image based on what you can see?
Between the center of curvature
Fantastic. Fantastic. So which means it is formed between the center of curvature and the principal focus. Now these are the things they are most likely going to be asking you in an exam setting. So, and again, in a calculational problem, when a question gives you information that aligns with what you are expecting to see, if you were to draw the ray diagrams, you may not even solve the problem before you can easily guess the answer from the options. Another thing is, there are some problems in which, while solving them, you ended up getting an answer that goes against your expectation. Immediately an answer that you got goes against your expectation, you know something is wrong somewhere. Let me give you an instance. Imagine you solve the problem and let's say the object distance was let's say a problem like this. Let's say we got an object distance, we have an object distance of, let's say, 50 centimeters, and you now ended up getting an image distance something like 60 centimeter. You know that something is wrong somewhere. Why? We expect an image distance that is smaller compared to the object. You get me? So in a situation like this, if you ended up getting an answer that is against your expectation, you can always tell that something is wrong and it will help you to find out. But if you are somebody who doesn't understand how to draw ray diagrams, you probably have a blank relationship. Do you understand that? You probably do not even know what to do at some times. Sure you get. So it's important for you to be able to guess what is happening sometimes. I hope you understand that. Are you with me? Alright, let's move on. So that's case 1. Now we also have case 2. For other cases, I may not have to draw ray diagrams for you. I will just state them. Case 2, because of time. Case 2, object on center of curvature. When you place the object on center of curvature, the image is one. The image will still be inverted. The image will be what? Real as well. The image we have, okay, is of same size as the object, same size as the object, and same distance, as the object. Then number 4, the image is formed back at the center of curvature. Now for you to understand these things, it is important you draw the array diagrams. Okay, now let me try and explain what has happened there. Okay, let me use this diagram. Just hold on. To make it easy, let me draw with lines. Let me draw with lines here. Say we have no, let me use okay. All right. Now say this is the principal axis of a curved mirror. Okay. Now let me also have this to represent the mirror itself. Just hold on. For you to get this, you need to be perfect. Like, especially, I mean, this particular case 2, where the object is at the center of curvature, you need to have a near perfect diagram. Okay. Now I have the mirror at the center here. Let me use this to represent the mirror. Okay, now this is the curved mirror here, a concave mirror. Alright, now say we have this as the, what's it called? The principal focus, and you have this point here to be the center of curvature. Can you see that? And this diagram is not perfect, but is near perfect. Now we have an object. We are considering a case where an object is actually standing on the center of curvature. This is the object here. Alright. Now, like I told you, you can use any combination of the 3 rules. So I will use any 2 combination here. Let me use rule 1, an object that is, a ray parallel to the principal axis. So I have a ray. I'm about to draw a ray that is parallel to the principal axis. I will start from the head of the object. So this is me drawing a ray parallel to the principal axis. Can you see that? Can you see that? So according to the rule, how should the reflection go? Who can tell me? According to the rule, how should the reflection go?
To pass through the principal focus.
Thank you very much. It should pass through the principal focus. So I will draw another line from here. Then I will make it go through the principal focus. Can you see that? So we've drawn that already. It's passing through the principal focus. Then I'm about to draw the second ray. Now this is our incidence for the first and the reflection for the first. The second one, I can decide to use rule 3 if I want to, my choice, or I use rule 1 if I also want to, my choice. Rule 2. Let me use rule 2. Rule 2. So I'm about to draw another ray. Ctrl V. But I want it to pass through the principal focus. Then also starting from the head of the object. Now based on what you can see, it's passing through the principal focus. Can you see that? Good. Then according to the rule, how should the reflection go? Tell me, how should the reflection go?
Parallel to the principal axis.
Thank you very much. So we have, I'll draw another array. I need to reverse this. Okay, so from here I'm drawing a ray parallel to the principal axis, so it goes like this. So based on what you can see, the second reflection is this. Now look at the first reflection, it goes this way. The second reflection goes this way. You can see their point of meet, right? Their point of meet is here. So which means let me clean this C from here so that we can see the image very well. Oh, don't worry, let me leave it there, but use a different contrast. Now the image is formed here. So you can see that both the object and the image are now what? Formed at C. So that justifies this statement I made here, that it is formed back at C. And number two, the orientation shows that the image is still inverted compared to the object. Then again, since as an observer you are going to stand on the left hand side and the image is formed at your side, it makes it what? Real. Then lastly, if you compare the size of the object and the size of the image, provided you draw a very neat diagram, you are going to have the same what? Size. They have the same size and they have the same distance. So this U here represents object distance between the object and the mirror. V here represents image distance. Let me ask a simple question. What would be the distance between the object? Okay, let me ask this way. If the object has, in this situation, has a distance of 20 centimeter, and then I ask you, at the end of the day when the image has been formed, what will be the distance between the object and the image? The distance between the object and the image. Option A, is it going to be 20 centimeter? B, 40 centimeter? C, 0 centimeter? D, 10 centimeter? What would that be?
0 centimeter.
That's correct. That's 0 centimeter. The distance between the object and the image is going to be what? 0 centimeter here, because they are both lying on the same point. Alright, moving on. So for other cases, I won't be drawing ray diagrams. I will just go into conclusion about the properties of the image formed. After this class, try and draw the ray diagrams yourself. Please just have to do that. So we have a case what? Case 3. Case 3, we have object between the center of curvature and the principal focus. So to make it easy, I'm going to make use of this diagram again. I'll make use of this diagram here. Let me paste it here. Okay, so now our interest is not on the object on the center of curvature, but on the object. Let me take this away. You may end up needing them. Okay, now see. Let me take this away. Okay, now watch. This point here is the is the center of curvature of the mirror. Then this point right in between them is what? Is the principal focus. Why this point here is the pole of the mirror. The case we are dealing with here now is the object here. is the object here. Object between C and what? F. So the image is formed. Who can guess the properties of the image is formed? What will be the properties? Who can guess? Let's start from the orientation. Do you think it's going to be inverted?
Yes, man.
Okay, that's correct. The image will be inverted. Let's talk about the size. Do you think the size will be same size as the object, diminished or magnified?
Magnified.
Okay, it will be magnified. That is as well correct. Magnified. Let's talk about the nature of the image. Will it be real or virtual?
Real.
That's correct. To be real. Okay, the last case, let's talk about the positioning. Where do you think the image will be formed? I'll give options like on the center of curvature, behind the center of curvature, between the center of curvature and the principal focus, and between the principal focus and the pole. Where do you think the image will be formed?
Behind the center of curvature.
That is correct. The image will be formed behind the center of curvature. In order to carry everyone along, I'll quickly do a simple ray diagram here. I already said I won't do that before, but let's quickly do that. It's not much of a problem. The object is here. I want to make use of rule 1, where a ray parallel to the principal axis, is drawn from the head of the what? Of the object. Come on. Okay, hold on. I need to adjust the magnification here, or else you won't be seeing anything. Nah. Just hold on. Yeah, perfect. Good. So we have this to be the ray parallel to the principal axis. Then from what you know already, it should go through the principal focus. So we have this. So this is the ray being drawn to pass through the principal focus. Okay, then wait, hold on. I think it's frozen. Just hold on. I need it to be perfect enough. Just hold on. Alright, let's just manage it that way. Then I need to draw another ray. We can draw a ray that passes through the focus. So I'll also do that from the head of the what? Of the object. I will just have to make it pass through the principal focus. Can you see that? Good. Then lastly, according to the rule, it should go parallel to the principal axis. So I will draw the line. I'll take this and make it go parallel to the principal axis. Let's extend that. So from what you can see, this point is the point of meet of the two reflected rays, this guy here and the one here. So leading us to conclude that the image is formed here. Now based on what you can see a bigger image compared to the object. So that ticks the box of what? Magnified. You can see the orientation of the object compared to the image compared to the object. it is inverted, so that ticks the box here. Then as an observer, you are standing on the left hand side of this mirror and the image is formed at your side. That ticks the box of what? Being real. And it is formed behind the center of curvature based on what you can see. That ticks the last box. So that. Then the last case here, case 4 was case 4. We want to treat a case where the object is what? Actually at the what? Principal focus. Where the object is at the principal focus, case 4. Now let's take this off so that we can just make use of the diagram, the same diagram. Okay. So we have object at what? F. Case 4, object at F. Object at point F. At principal focus. Principal focus F. Okay, now based on this, I will draw the position of the what? Object. So we have this is the position of the object now. So I'll draw a ray parallel to the principal axis. This is what we have here. So we already have a ray that's what? That goes parallel, this is the incidence, this will be the reflection. Now watch. We may not be able to make use of rule 2. Yes, ma'am. Now we can't make use of rule 2. Why? Because the object is directly standing on the what? Principal focus. It won't be nice to make use of rule 2. So then we can make use of rule 3. And what does rule 3 state? Rule 3 states that if you have an object that passes through, if you have a ray that passes through the center of curvature, it always go backward, undeviated. Okay, now see, I'm about to draw a ray that will pass through C. This is a ray that passes through C. Now it's not enough to just draw it to pass through C. It has to touch the head of the what? Of the object we are dealing with. Okay, this is a perfect condition. So it's touching the head and it goes, now look at the way it goes. It goes parallel. It goes parallel. Now you can see that if this is the incidence, according to the rule, how should the reflection go? According to the rule. Somebody tell me. According to the rule in this case, how should the reflection go? It should go out.
Along the same path.
Thank you very much. It should go along the same path of incidence. So you have this to be the reflection. Now watch, this is reflection 1 right here, R1, and reflection 2 right here, R2. Based on what you can see, can they ever meet? Based on what you can see, can those two lines meet? Fantastic. Those two lines have no chance of meeting, or if we say they will meet, it will definitely be at infinity. So our conclusion is that what? Image is formed at infinity. Image is formed at infinity. Image is formed at infinity. So please take note of that. Alright, then case 5. Case 5. Alright, let's adjust this to case 5. Case 5, we have the object between the, what's it called? The object now between the principal focus between the principal focus object between principal focus and the pole so let's say pole P. Alright, so we're about to tell the properties of the what image font if the object is repositioned from where it was to another point. Okay, so now we have an object somewhere between. Now I'm placing it here. So we have an object here. Let me use a better color to display that. This is an object here. It's standing between the principal focus and the what? And the pole. So, still making use of rule 1, I will draw a ray from the edge. Can you see that? Then the next, since this is incidence, then we shall have what? Reflection. The reflection is already there, so that has been taken care of. So the next is to make use of rule 2. Rule 2, we can draw a ray that passes through the what? Center of curvature. That passes through. Okay, let me make use of the one that passes through the center of curvature. So meaning I have to adjust it to touch the earth. Can you see? Good. Something like that. Okay. Let me adjust this side well. Good. Something like this. Fantastic. So based on what you can see, towards the base here, the line seems to be diverging, while towards the top here, the line seems to be what? Converging. Don't forget that along this line, both the incidence and the reflection are there. So since it is seeming to be converging here, so this is going to be the only possibility of the what? Two rays meeting themselves. So I will just extend that like that. Good. So based on what you can see, the two rays meet somewhere around here. Now start talking. Let's talk about the size. What can you say about the size? Diminished or magnified?
Magnified.
That's correct. It is magnified. Magnified. Then number 2. Let's talk about the orientation. Is it erect or inverted? That's correct. What another name can be used for erect? Fantastic. Upright. Then number 3. Let us talk about the nature of the image. Do you think this is real or virtual? Fantastic. Because as an observer, you are to be here. So if an observer is here, the image is formed. No, I made an error. If an observer is to be here. If an observer is here, the image is formed at what? The opposite side of the observer. An observer, you remember, an observer cannot stay behind the mirror. This is definitely the back of the mirror. As it is the back of the mirror, it would be stupid for somebody to stand behind the mirror. So, you're right, it is virtual. So So how do you explain the positioning of the image? Okay, let me give you options. Options like it is formed on the principal focus, B, it is formed behind center of curvature, C, it is formed behind the mirror. What do you think the answer should be?
Behind the mirror.
That's correct. So image is formed behind the mirror. Behind the mirror. Alright. So that's what we have. Then we have the last case. The last case, which is case 6. Case 6 is object at infinity. Object at infinity. At infinity. So we are considering a case where an object is far away from the mirror in question, and we are looking for the possibility of the image formed by what? The mirror itself. Okay, so the object is not formed in the, it's not at the vicinity of the mirror. So let me clean this off first. Okay, now the only way we can represent an object from an infinity is to use parallel lines coming from somewhere. So I will make use of two parallel lines, and I will ensure that the two parallel lines pass through two main points on the principal axis. One is already passing through the center of curvature. I want the other to pass through the principal focus. Good. Now see. So I have a line passing through the principal focus and another passing through the center of curvature. Obviously, the two lines are parallel to themselves. Okay. Now, from what you know already from the rules, a ray that passes through the center of curvature will be reflected back along the path of incidence. But that won't be the case for the principal focus. For the principal focus, a ray that passes through F, let me shift this a bit so that it can pass through the F properly. Alright, that's a perfect representation. So we have incidence along this path. How should I draw the reflection? Somebody tell me. How should I draw the reflection? This one, the reflection of this particular ray. How should it be drawn?
Maybe back to the mirror.
I expect it to say parallel to the principal axis. That's rule 2. A ray that passes through the principal focus should go parallel to the principal axis after reflection, right? Okay, so that's what you should do. So I'll draw a ray that passes through what? This. So based on what we have here, we can tell that what? This is the point of meet of those two lines. So you can see that the line meets at the principal what? Focus. So which means the image is formed at the focus. Now, in terms of nature, we can tell that the image is also real. Are you there? because as an observer you are going to stand on the left hand side of the mirror, so the image is real. Now what you may not be able to conclude is if the image is actually inverted or real, because we don't have an idea of the orientation of the object. And again, what you may not be able to conclude here is the size of the image. But if you were to ask me, it is more likely going to be diminished. You remember that an object that is very far away, when observed from a far distance, seems to be small. Do you get the idea? If you are looking at an object, imagine somebody approaching you from a very far distance and you are seeing the object seems smaller compared to its original size. Is that true? Are you with me?
Yes, sir.
Okay, so by that logic we can say that what the image of the object is more likely going to be what, diminished when compared to the object. But we can't conclude that because we don't have access to the what, object. But the main thing you need to know here is that the image is focused, it's formed at the focus, and it's also real. Alright, conclusion now. Case 1. When the object is positioned behind the center of curvature, the image is always what? Real, inverted, diminished, and formed what? Between the center of curvature and the pole. Center of curvature and the mirror and the principal focus. Let me go back to the case 1. This is it here. When an object is behind TC, the image is inverted, real, diminished, and formed between what? Center of curvature and what? C. This is the exact diagram that demonstrated that. Then for case 2, when the object is on CC, the image is real, inverted, having same size as the object, and formed back at what? CC. And this is a diagram demonstrating that. For case 3, when the object is between C and F, the image is always inverted, is magnified, real, and behind CC. And that's a diagram demonstrating that. Case 4, when the object is positioned at the center of curvature, the image is always formed at infinity. You don't have any other properties of the image, just that. Case 5, when the object is between the principal focus and the pole, the image is always virtual, magnified, erect, and will form behind the what? Mirror. And the last case, when the what? Object is at infinity, the image is always formed back at what? At the focus. So these are the things you need to know about what? About ray diagrams, and they will help you in solving some problems. Okay, I will just solve like 5 questions with you, then we'll call it a day. Okay, looking at this question, we have a concave mirror having a radius of 24 centimeter produces a real image 4 times the size of the object. The question is asking you to find the distance of the object from the mirror. Okay, now this is a concave mirror. So what are the things they supply there? The first thing they gave here is the radius of curvature, so which means R is equals to 24 centimeter. Then radius of curvature is twice what? Focal length. So which means your focal length here is going to be 12 centimeter. So again, they use statement like produces what? A real image, which is what? 4 times the what? Object size. And based on what you can see, that means the magnification is what? 4. Or if you don't want to look at it that way, you can say, since they said it produces a real image that is 4 times the size of the object, it means image distance is going to be 4 times what? Object distance. U has to do with image, V has to do with image, U has to do with what? Object. They said the real image is 4 times the size of the object, which means the V for the image is 4 times the U for the object. And based on what this question is asking, he said we should look for the distance of the object from the mirror. That statement means what? Object distance, because they said what? Of the object. If they said of the image, that would have meant image distance. So which means you are looking for what? U. So U is what you are looking for. You just go ahead and use the image formula, mirror formula. 1 over U plus what? 1 over V equals to what? 1 over what? F. So in this case, you have 1 over U plus V is given as what? 4U equals to what? 1 over. Now, our F, is it going to be positive or negative? It is positive because they made mention of what? Concave mirror. Alright. So this is going to be 12. So in that case, somebody tell me, what's the LCM here? Tell me, what's the LCM?
4U.
4U. Or better still, multiply through by 4U. What do you get? Multiply this by 4U, what do you get? That will be 4, do you agree?
4.
And if you multiply this by 4U, what do you get?
1.
1. Then that gives us what? 4U over 12. Do you agree? So from there, we have it as what? 4U is going to be 12 times 5. And 12 times 5 is what? Is 60, right? So if you divide through by what? 4, U is going to be 15 centimeter. So that tells you that what? U is 15 centimeter. Okay, now
Sorry, sir. This is how it equals to 4U.
okay, good. Now look at this line. The question says produces a real image that is 4 times the what? Size of the what? Object. Can you see that? Do you get it?
Yes, sir. Thank you.
Alright. So is there any other question on this before I move on? Alright, I'll assume you understand that. So let's take another question. I want to believe you can see this question. Now I'll give you like 60 seconds to attempt it yourself. Second. 40. 50.
40 cm.
Okay, you got 40 centimeter. Okay, we'll check it together now. So the question says an object is located at a distance of 20 centimeter from a concave mirror. Since they said object and they gave you distance, that's object distance, which is denoted what? U. So we call that 20 centimeters. Then they gave the radius of curvature of 30 centimeter. 30 centimeters. So the question is asking you for the separation between the object and the what? Image. So it's asking you to find something like u minus v or v minus u. I'll put it in absolute sign. Okay. For somebody who is used to ray diagrams, I can easily tell the position of the what image based on this information supplied to me. Okay, now watch. Something like in this question they gave you radius of curvature as 30, that's r, which means the focal length of the mirror is 15 centimeter, and they give you an object distance of 20. For somebody who is used to ray diagrams, I can tell that what this is the principal focus, this is the center of curvature, the gap here is 30 centimeter, and the object being at 20 centimeter means the object is positioned between the C and F, and the image is usually behind what C, and what is usually behind what's it called, behind the center of curvature. So if this is 20 centimeter, I am expecting a value that is bigger than 30 centimeter for my V. But mind you, what we are looking for is not just V, we are looking for the gap between what V and what and this. So our answer is most likely going to be between this and this. But why am I thinking what? It is going to be something like 20 centimeter just by eye inspection. But let's solve the question. So the first thing you do is to find u. Since r is given as this, it means f is going to be 30 over 2, which is what, 15 centimeters. So you say 1 over u plus 1 over v equals 1 over f, which then means we have 1 over 20 plus 1 over v, which is unknown, equals to 1 over 15. Now there is a problem. Okay, watch, this is concave mirror. Okay, then we're on the right part. If it were to be convex mirror, there will be a need to negate the what, this 15 here, but we can't negate it here because it's concave. So from there we have 1 over v equals to 1 over 15 minus 1 over 20. The LCM there is going to be what? What do you think the LCM will be? Anybody? They are gone. So we can use 60 as the LCM. 15 in 60 is 4. Then 20 in 60 is 3. So we have 1 over v equals to 1 over 60. V is 60 centimeter. Then Moid is right, the answer is 40, because what you should have is v minus u, which is the distance between the image and the object. That gives us 60 minus 20, and that's what, 40 centimeters. So that's very much correct. So 3 more questions to go. Okay, no one has an answer to this yet. All right, let's solve it together. All right, now first thing I needed to look at is the name of the mirror mentioned there. I need to shine your attention to the convex mirror they said there. So convex mirror, that's a reminder that the focal length is going to be negative, or you say it has what, a virtual focus. And I'm not giving you the ray diagrams for convex mirror. For convex mirror, the nature of the image is always what, something that is summarized in the acronym VED, virtual, erect, and diminished, irrespective of the position of the what, object. So meaning we don't need to have a case study for convex mirror. Meaning Either the object is positioned further away from it, closer to it, wherever you position it, the image is always virtual, erect, and diminished. Please take note of this for convex mirrors. After this question, I will give you a ray diagram to emphasize that. Now back here. So the question says a convex mirror, take note of that, produces an image which is what? 1/4 the size of the object. They say the image V is 1/4, that's 1/4 the size of the object U. Now it is important you take note of this statement, virtual. The image is always virtual, so I must put minus here. Without a minus, you are going to get what? A wrong expression. Now, they now said if the radius of the what? The radius of curvature of the mirror is 32, R is given as what? 32 centimeter. Let me be more specific, convex. 32 centimeter convex. That automatically implies that what? Our focal length is going to be minus, don't forget it's a convex mirror, minus half of the what? What's it called? Of the radius of curvature, and that is what? Minus 16 centimeter. What do we need? We need the distance between the object and the image. We also need V and what? And U. I mean, we need the gap between V and U. For you to have a perfect understanding of this, I think there is a need for me to do the ray diagrams. Okay, let me solve this question first. I'll come back to it. So first thing first is to try get U. We have 1 over U plus 1 over V equals 1 over F. So which means I can say 1 over, what's my U? I don't know, plus 1 over V. 1 over V is minus 1 over 4U. Then equals to what? Minus 1 over what? 16. Let's rewrite this. This as good as me writing is as 1 over U minus 4 over U equals to minus 1 over 16. So U is the LCM, so I have minus 3 over U equals to what? Minus 1 over 16. So from there, U is going to be 16 times 3, that's 48 centimeter. That's our U. But what do we need? We need the gap between U and V. If U is 48, what is V? V is going to be what? Minus 1 over 4 into what? Into 48. Divide 48 by 4. That will implies that what? V is equal to minus 12. Minus 12 centimeter. Now, what's the gap between what? Between them? The gap between them is going to be what do we have? V plus absolute value of V, U plus absolute value of what? V. That gives us 48 plus 12. That's 60 centimeter. Now we explain why it is 60 centimeter using ray diagrams. Now let me go back to this ray diagram I drew here, but this is for concave mirror. Now I will redraw this for convex mirror. Alright, I want to draw the ray diagrams for convex mirror so that you'll have a perfect understanding of what is happening exactly for convex mirror.
Sorry, Samantha, your voice is
And what?
broken.
Say that again.
Your voice is breaking. I can't hear you say like that.
Oh. Okay.
I
My
said
voice.
your voice is shaking.
No problem. No problem. What's going to happen is this: the class is on recording. I will still drop the link in case. Do you get that? You miss anything? You get? All right. Moving on. So we are considering a case of convex mirror. Convex mirror. That's a ray diagram for convex mirror. Okay. So let me take this away from here. Okay. Now say we have this to be a convex mirror here. So you can see that this convex. Shading this side of this mirror means that what? The observer needs to be what? At this side. Okay. So where is my principal focus? If we were to complete a whole circle for this thing, the circle would have been something like this, right? Which means the center of curvature would have been somewhere around here, and the principal focus would have been somewhere in between here. Good. So I have the center of curvature and the principal focus. This point here represents the pole of the mirror. Now, definitely object can only be here. I'm not even talking about observer here. Any object you want to talk about should be here. An object cannot be at the back of the what? Mirror. So, say you have a lady, let's make use of a lady, standing in front of this convex mirror. Good. Standing in front of the convex mirror, then we want to draw ray diagrams that will help us interpret what is happening. So first thing, I want to make use of rule 1. And what does rule 1 state? It states that if we draw a ray that is parallel to the principal axis, so I will draw a ray from the head of the what? Object. I will draw it parallel to the principal axis. This is it. Then what do we then do after that? According to the rule, it states that it is going to what? Reflect. The reflection is going to pass through the center of curvature. Now I won't just draw a line that will go through this. Oh, hold on. Hold on, my system is just somehow. Alright. So I won't just draw a ray that will just go this way. No, it's not as simple as that. You can't just draw a ray like that. Don't forget, it's a mirror. It is not a lens. The job of a mirror is to reflect. The job of a lens is to refract. So in this case, I can't just draw it that way to be wrong, but I will draw my ray as though it is coming from that point. Now watch. I will draw a line. Now I'm just hold on. So I'm drawing a line from this point. So you can see how I've directed it. I've drawn a line as though it is coming from F and directed that way. Can you see that? So which means if the reflection incidence goes like this, after meeting the mirror, it should go what? It should go this way. So I've used rule 1. Now it's time to use rule 2. Rule 2 means I will now draw a ray that is going to pass through F. Alright? So, starting from the head of the object, I have this. So, my ray has to be drawn in such a way that it is passing through what? F. This is what I have. But don't forget that it's not a mirror. I mean, it's not a lens. It's not going to go all the way here. I will draw it as though Okay, let me do it like this so that you understand it. But it's not going to be extended up to that point. It's only seem to be extended to that point. This is what we have. The ray will go like this, and after getting here, it will get reflected parallel to the principal axis. So I'll draw a ray parallel to the principal axis now. So it gets reflected. We have something like this. Okay, hold on. This is what we have. From this point here, you will draw a ray parallel to the principal axis. So, but I have to extend it this way so that you see the point of it. Good. This is what we have. Incidence goes this way. The reflection goes this way. Can you see that? So the point where reflection 1, which is this, and reflection 2, which is this, meet, is definitely at this point here. So because they met at that point, it helps us to conclude the position of the image. So if you compare the image to the object, what can you say? What can you say about the about the image?
Diminished.
Okay, it is diminished. What about its orientation, erect or inverted? Okay, it is erect. Then virtual or real? Virtual. So this is a conclusion that the image is always virtual, erect, and what? Diminished. So now what? See the object distance. And from here to here we have the image distance. So if somebody is asking you what's the gap between object and image, you can see that it is a direct sum of u and v. Can you see that? So that is my exact reason when I added u and v here. So don't forget that the v here being negative is only informing you that the image is virtual. So that doesn't mean you have to put the negative here. So what I did there was 48 plus 12, and this gives us 60 centimeters. Okay. We are supposed to solve 2 more questions, but I don't think I'll go 2 more. We'll just solve one question on quality there. Okay, we have a question here. I will enlarge it for you to see it properly. Now look at this question here. It says an enlarged object is to be produced on a screen in front of a concave mirror. The object must be positioned where? Now, take your time. I give you 40 seconds to look at this. Think of radar guns.
Between the principal focus and the center of curvature.
Between the principal focus and the center of curvature. That's correct. Wait. That's false. Let's see that again. Wait, did you say principal focus and the center of curvature?
Yes, the last option.
Yeah, that's correct. Because For you to produce an image on a screen, the image has to be real. That's the first fact. And two, we want the image to be enlarged, which implies that we'll be making use of which case? Case 2. No, case 3. The case 1 I had with you was an object position position behind the center of curvature. Case 2 was the object on center of curvature. My case 3 was the object position between the center of curvature and the pole, which implies that the image will be magnified, magnified, it will be real, inverted, and form behind the center of curvature. So let me navigate to the ray diagrams that explain that. That was case 3, this particular case. Right. On this note, we'll be calling it Eden, and thanks for listening. Is there any question for me?